Greetings, budding mathematicians. I have a treat for you today. In this video, we are going to do a magic trick, and I'm going to teach you how to do it. That magic trick is called the remainder theorem. It's an amazing theorem in mathematics that tells you when you're about to do polynomial division that how to compute the remainder before you even divide. Fantastic. Let's go see how it works. So the example we're going to do is we're going to divide this polynomial and by this polynomial. Now I just made up a polynomial and made up an expression of the form x minus k. All right. I invite you to do the same thing. Make any polynomial. It doesn't even have to be second degree. No matter how long. You get fifth degree. That's fine. And then pick any expression of this form. You can make this number anything you want. You can make it a 7, an 8. You can make it a negative number. You can make it an irrational number. You can make it pi if you want to. Any number you want. And the remainder theorem is a magic trick that shows us what the remainder is going to be. So I can already tell the remainder is going to be 12 when we do this division. How can I see that so easily? Well, the remainder theorem tells us that all we have to do is take this number here, that's our k, and plug it into this function here. This is f of x. And I evaluate this function at 2, I get 12. So I know the remainder when we do this division is going to be 12. Let's carry out the division and see that we're right. All right, so we're going to take x minus 2, and we're going to divide that into our polynomial. Okay, so I ask myself, how many times does x go into 3x squared? Well, it goes into 3x times. It goes in there 3x times. Now, by the way, if you haven't watched the videos on polynomial division, stop this video right here. Stop it right here. Go watch those videos and then come back, because otherwise you're not going to have a clue what's going on. All right, so if you can't do polynomial division, this will just be a mystery to you. Okay, now that you've watched those videos, you've come back. We're going to take this, multiply it by this expression. All right, and we're going to subtract these. Subtracting is the same thing as adding the negative. So I'm just going to negate everything, and I'll add, right? So these cancel out, and I get 4x plus 4. Now I ask myself, how many times does x go into 4x? Well, it goes in there 4 times. Now I multiply, and I get 4x minus 8. And again, I'm going to subtract. Well, that's the same thing as adding the opposite. So I'll just make everything negative. I'll just negate everything, add these down, and I get 12, just like we said. Just like we said. I knew the answer was going to be 12, and voila, that's exactly what we got. It's an amazing trick, but it's also a great trick to know because you can use it as a check to make sure your division went according to plan. We would know if we made a mistake here. Now, by the way, how do we write the final answer? Well, if I wanted to express this division, what I would do is write my answer here, 3x plus 4. If I didn't get a remainder, if the remainder was 0, I would just write that. But since I got a remainder, what I do is I add to that the remainder term divided by this term. So I take 12 over x minus 2. And that is how I would express this division. So what we're going to do next is we're going to prove this. We are going to prove that no matter what polynomial I pick up here, and no matter what number I choose over here, that the remainder will always be what I get when I plug this number into the polynomial. Okay? So to prove this, what I'm going to do is I'm going to take an arbitrary polynomial, so just call it f of x. All right? And I'm going to divide it by x minus some number. So let's call that number k. And we see what we get here. We get a polynomial over here, so let's call that q of x. Q stands for quotient. And I get the remainder up here, and I divide by x minus k over here. So we know whenever we do polynomial division, we're always going to get something that looks like this. You just saw it happen. Okay? Now, I'm going to go ahead and on the right-hand side, I'm going to do a demo with a particular function, just like we did up here. But I'm going to choose a new function. All right? So let's bring this up. This time for my polynomial, and you know what? I invite you, choose any polynomial you want. Pick one out of a hat, or pick your favorite polynomial. All right, I'm going to pick x squared plus x plus 1. Right, but you could pick the most wild, crazy, zany polynomial you want. You can go to the 5th degree if you want. You can go to the 100th degree if you want. Doesn't matter. And we're going to divide by, oh, I don't know, I'll do x minus 3 this time. Now, what do I get here? Well, I know I'm going to get some expression plus r over x minus k. I mean, we just saw it happen. All right? So whatever polynomial you picked and whatever number you picked up here, go ahead and go through that division. All right? I'll do it over here. So we're dividing x minus 3 into x squared plus x plus 1. X goes into x squared x times. So when I multiply x times this, I get x squared minus 3x. I negate and I add. All right. Now I ask how many times does x go into this number, this term? Well, it goes in there 4 times. So I add 4, multiply. I get 4x minus 12. I negate and I add, right? And the number that we get down here is our remainder. Now you can see what it's going to be, right, when you add these. But I'm going to leave it as r. So what we see is that the answer is this, x plus 4 plus r, divided by this term here. So I've expressed this abstract stuff in terms of an explicit example over here. All right, and we're going to find out what r is, even though you can see what it is right here. All right, so my claim is, the claim that we're trying to prove is that that remainder is going to equal f of k. All right, so in other words, we're claiming over here that r is going to equal f of 3. My k is 3 here, right? So, and I can actually compute what that's going to be. F of 3, you could plug 3 into this expression and you can see what it's going to be, right? But let's see why it is. So let's do it in the abstract sense over here. Okay, so we want to show that r equals f of k. So let's take this expression and solve it for r and see if we can get f of k out of it. All right? So if I want to solve this for r, I probably want to multiply by its denominator. So let's multiply both sides of this expression by x minus k. All right, when I do that, the x minus k's cancel on the left, x minus k distributes on the right, and then cancels off beneath the r. So what I end up with is this. Let's do that same thing on the right with the explicit polynomials. So I'm going to multiply both sides by x minus 3. They distribute on the right and cancel on the left, and they cancel on that term over there. And so what I get is this. All right? Now, what am I trying to compute? I'm trying to show that r equals f of k. Well, let's plug in the k for x. We're going to need to do that. So if I compute f of k, what do I get? I get q of k times k minus k plus r. Or in the example over here, f of 3 here, just like we wrote on the left, right? And what do we get here? We get 3 plus 4, 3 minus 3 plus r. Okay, so let's go back over here and see what we can simplify this as. Well, if you notice, k minus k is 0, right? So f of k equals q of k times 0. Fantastic. I love 0. 0 is great when it shows up, unless it's in the denominator, right? Okay, but over here, what are we doing? Well, we have our f of 3. We're just simplifying the right-hand side. I got 3 plus 4 is 7. 3 minus 3 is 0 plus r. So you're seeing that same thing in abstract sense happening over here with specific numbers. All right, well, what can I say here? Well, q of k times 0 is 0. So it's gone. So we see that f of k has to equal r. That's exactly what we were trying to show. Let's see how that plays out in the explicit example. 7 times 0 is 0. 0 plus r is r. So I can see that r is f of 3. And yes, if you computed it out, f of 3 is 13. And so we have proved the remainder theorem.